Yeah. Good afternoon, everybody. Today's session will start off. Basically, we want to discuss in today's session is the how we can use advanced statistics in analytics, and primarily I'll focus today on certain test of hypothesis, primarily to test whether the population mean is equal to a particular value, or we would be comparing the means of different populations and use techniques like t-test, ANOVA tests in doing that. Okay, the data which we will work with, I'll just bring the data to the SAS environment. See, in this data we have certain patient level information, in terms of, say, there are about 90 patients, and these groups of patients, for them we have these variables captured like age, weight, heart rate, the two blood pressures, and their duration of operation and duration of anesthesia. And also, now these groups of patients were given two different kinds of drug, group 3 and group 2. These are two different kinds of drugs which are being given during the operation, and the objective will be to monitor these parameters across different time points. So for example, 15 minutes during the operation, 30 minutes during the operation, 45 minutes till 1 hour during the operation, 75 minutes during the operation, and finally the post-operative figure. Okay, so we'll be working with this data. Now suppose we want to test the hypothesis that, see, the generally the normal blood pressure level we keep at around 120. Okay, so we would like to see whether this group of patients, the blood pressure level is at 120 or not, the standard level. Now for these kind of tests, when we are working for checking for a univariate variable, there is one variable we are trying to test whether the mean is a particular value or not. For that we generally use what we call the one sample t-test. So let's see how it works. Now proc t-test is what works here, and the data is c dot data 1. The variable for which we'll check is SAP pre-op. If you're not certain what is the variable name, we can just open the column and check it, and we have to give a test value. So test value h0 is equal to 120. Now if we run this, let's see what we get. Okay, now if we look at this, the output, now these are the sample characteristics. Now the sample mean is 121, that is in this sample the total average blood pressure is 121. Now these are the, by default, the 95% confidence intervals. Okay, so this is the lower interval, this is the higher interval. So these are the 95% confidence interval for mean. Similarly, I get the sample standard deviation and their 95% confidence intervals. Now the p-value comes here. Now this p-value, if it's higher than the alpha level, we accept the hypothesis. If it is lower, then we reject the hypothesis. Now suppose the alpha level is at 5% or 1%, so is at 5%. So now if you look at this value 0.4382 is much higher than 0.05, which is the alpha level. So we accept the hypothesis to claim that the population mean from which this sample has been taken for blood pressure, the population mean is 120. So we end up accepting the hypothesis. Similarly, if we had taken some other hypothesis, we might have rejected that. For example, if we had taken a hypothesis that the population mean is 140, then we might have rejected that because the p-value, see here, is extremely small. So in that case we reject the hypothesis to claim that it is not 120. So this is the one sample t-test which generally works. Let me save that data. So we test the hypothesis that a particular population mean is equal to particular value. Okay, now when we check for equality of two population means, that's where we use the technique called the independent sample t-test or unpaired t-test. Now suppose the hypothesis in this case we'll check is whether the mean blood pressure or some other variable is same across the two groups. Now you can see there are two groups of individuals. So suppose I would like to check whether the blood pressure at 15-minute interval is same across the two groups or not. Okay, so if you want to check this, so this means that we are trying to test the hypothesis whether the mean of SAP underscore 15, which is the blood pressure after 15 minutes, is same across the two categories, that is the group which is having two categories. So if we run this, let's see what we get. Okay, now here we first get some sample characteristics, and if you can see the sample characteristics, they're fairly the same. Okay, the sample mean for the two groups are fairly the same, and also the standard deviation, and we end up accepting, and if you look at the p-value, it is extremely large. So that means we are accepting the hypothesis that the mean population blood pressure after 15 minutes is same for the two groups. So group 2, these are the sample characteristics, sample parameters, whereas for the population, if I want to check the hypothesis whether the mean of the blood pressure is same across the two population, yes, the p-value is extremely high, and we end up accepting the hypothesis that the population mean blood pressure is same after 15 minutes, whether for group 2 as well as group 3. This we can check for some other variables also simultaneously. Now if we check for say some other variable, say so we get for two particular variables, we check the same hypothesis. One is the SAP, other is the DAP, and we get these p-values are what we should look at where to accept or reject the claim. Yes, both of them are having extremely high p-values, hence we end up accepting the hypothesis that the mean blood pressure, both the systolic as well as diastolic pressure, is same for the two groups. So this is my independent sample t-test, and it can only be used when the variable for which this independent sample t-test is primarily used to check whether the mean of a variable is same across two independent populations. So here we could apply that in a data like this where the variable group has only two categories, okay, which is my group 2 and group 3. Now but suppose there are more than two categories for any particular variable, then we cannot use this unpaired t-test or independent sample t-test, but we have to use the ANOVA test. Okay, now in order to use the ANOVA test in this data, suppose I create three groups based on this blood pressure. Okay, so let me create three groups. So I've created three categories based on the blood pressure. One is less than equal to 120, one is 120 to 121 to 140, and one is more than 140. So if I I've created this particular variable in this data, and if I look at the distribution of this particular variable, let's see how it works. So there are 51 observations in this group, 33 observations in this group, and 6 in this group. Okay. So now if I want to check whether the average weight is same for these three groups of blood pressure. Okay. So what we do is, now from where does this term ANOVA comes? ANOVA actually means analysis of variance. If I the full form of this, so what exactly is trying to do is that, see, there is a variable called weight, and we are trying to see whether it is causing or it's the variation is the BP variation is due to the weight level or not. Okay, or on the contrary, suppose if I do something on the weight, instead of creating the my categories on my BP, if I create my categories on weight or age, so let's create some categories on age and weight. Okay, so we got these age groups, as well as let's create something on the weight levels also. So I'm creating two variables, one on the age, the other on the weight. So if age is less than 30, then it's group 1, 30 to 40, 31 to 40 is group 2, more than 40 is group 3. Similarly, weight is below 50 is group 1, 51 to 60 is group 2, and above 60 is group 3. Okay, so I create these columns, and now if I look at the distribution of these two variables, we see that group 1, 2, 3, these are the distributions in terms of, so this is my age group 1, 2, 3, weight group 1, 2, 3. Now if I want to see whether the blood pressure varies across weight, so let's see. Now as I was saying that ANOVA, the term originates from analysis of variance. So see, there is a variable called blood pressure. Now the objective of ANOVA will be to, and it has some intrinsic variation. Now the objective of ANOVA will be to identify the cause of variation. Now whether a variable called weight can be used to attribute the, or can be held responsible for the variation in the blood pressure. For that we need to check the ANOVA test. So if I run this, if I look at the p-value, we see that there is not enough Now if the p-value is more than my alpha, so what was the hypothesis? Hypothesis was that the blood pressure is same across all the weight groups. And since here if I look at the p-value, the p-value is higher than 5%, which I have taken as the alpha level. And so if it is higher than the alpha level, we end up accepting the hypothesis to claim that there is not significant variation in weight level across the significant variation in the blood pressure level across the 3 weight groups. Okay, similarly I could have checked it for the age groups also. Okay, so I check it across the 3 age groups also. And we see that again here also we don't see any significant variation across the 3 age groups. Okay, now just by looking at the p-value, sometimes we may not be able to get quite a good picture. So what we may also interested in doing is checking up the means of the variables across these weight groups. So if I do that, this we discussed in our last webinar, how we can do a proc means and with class statements and things like that. So if I look at the mean levels for the across age group, we see that they are fairly similar. Same thing here also. Okay, so this actually is contributing to the fact that there is no significant variation across of the blood pressure across the weight group as well as the age group. Now we may also tempted to see if here we are looking at all the 3 categories at one go, but suppose I want to check only categories 1 and 2, because if I look at the mean values, the 1 and 2 seems a bit different than the others. So if I want to check only groups 1 and 2, that also we can do. If I exclude the 3rd category, then we can check only groups 1 and 2. Okay, and if I look at here, we are only taking up groups 1 and 2, and if I look at the p-value, it's a bit lower than what we got earlier, but still not low enough to get a significant difference across the 2 groups. Okay, similarly if I want to look at for the age group also, if I wanted to look at the groups 1 and 2 or 2 and 3, same thing we could have done. So we are checking between groups 2 and 3. And if you look at here also, the p-value is low, but again not low enough in a case of 5% alpha to reject the hypothesis. So in any case, we are accepting the hypothesis out here that the blood pressure is same across the weight group as well as the age group. Similarly, this technique we could have applied for any other variable also, and we could have checked whether there is a significant variation in that particular variable across different population groups. Now this particular technique is called one-way ANOVA. The reason why it's called one-way ANOVA is that Here we only look at one particular population. For example, we are at one time we are only looking whether the blood pressure is varying across the weight group or blood pressure is varying across the age group. But if I want to look at the two of them together, that is simultaneously, if I try to assign the variation in blood pressure due to weight group and age group, then comes the case of two-way, three-way or n-way ANOVA. Now here we are giving example with two-way ANOVA, but it can be extended to any number of cases. So if I want to look at here the impact of both of them simultaneously, so I am taking in both of them simultaneously, okay, the weight group as well as the age group. Please everybody, can they mute their mic because there is a lot of sound happening in the background? Anybody who is on mic, please mute it. So now if we want to check the impact of both these population groups simultaneously, this is called a two-way ANOVA. If I was taking one more variable, it would have been three-way ANOVA and so on and so forth. So here we will actually generate two p-values, one for the weight group, second for the age group. Now if I run this, we see we get two p-values, one for age group, the other for the weight group. And as earlier, we get that there is no significant difference in the blood pressure across the weight group as well as the age group. Okay. Now whenever we have our case of more than one-way ANOVA, that is when we are checking the impact of more than two population groups, then we can also check their interaction impacts. For example, if I want to check the impact of the combined effect of each weight group and age group, okay, so an example can be, say, with this the one-way ANOVA we check the average salary same across three cities. With two-way ANOVA we check the average salary same across cities and gender. With interaction we check average salary same across city, average salary same across gender, as well as average salary same across every combination of city and gender. So this is the combined or the interaction effect comes through this component, and here again we get three p-values, one for the weight group, one for the age group, and third for the combined impact. Okay, so these p-values will help us to accept or reject the respective hypothesis which we have for each one of them. So this basically is the discussion on the ANOVA, okay, which checks, and by this we can check unlimited combinations of population groups and their interactions, and we can go on checking whether the average salary is same for three cities, gender, educational qualification, or a combination of them. So all these things can be done using this ANOVA test. Now the final topic which I would like to discuss today is called the pair t-test. Now how the pair t-test works is, it works for if I want to check the mean of two variables. Now so far what we have done is we have checked the mean of one variable, equality of mean for one particular variable, but across either one particular population or two particular population or more than two population or more than two population groups. But suppose I want to check the mean of two variables v1 and v2. Okay, now ideally speaking this v1 and v2 should be somewhere related, otherwise the checking will not make any sense. And especially in a data like this where we have say we have the preoperative figures as well as the figures at 15 minutes, figures at 30 minutes, and we would like to see whether there is a significant variation in this particular blood pressure across time. So that's where this kind of pair t-test comes into play. So if I want to check, say for example I want to check the preoperative level blood pressure with the 15 minutes blood pressure. So we check like this. So I am trying to test the hypothesis that mean of SAP pre-op is same as mean of SAP after 15 minutes. So if we check this, we get that the p-value is not very low, it's pretty high. Hence we end up accepting the hypothesis that mean blood pressure level is same at 15 minutes interval after operation as compared to the preoperative level, though there is a slight increase. If you can see that SAP pre-op minus SAP 15 is bit negative, so there has been a slight increase, but that increase is not significant because the p-value is not more than my alpha level. Okay, so now similarly I could have checked other combinations also. For example, if I want to check the heart rates like this, but for heart rate if I see, there is a significant difference, and if I see that heart rate after 15 minutes is significantly lower than the preoperative heart rate, and the p-value is extremely small, so we end up rejecting the hypothesis to claim that there is a significant difference in the heart rate after 15 minutes from the preoperative level. Not only a difference, by looking at this sign, what we can see that this is HR pre-op minus 15 is negative. That means heart rate, there has been a significant increase. So there has been a significant increase in the heart rate level at 15 minutes during operation as compared to the preoperative level. Okay, so this is the paired t-test, and now if I want to check this separately for the two groups, what we can do is we can first sort the data by the group variable, and then we can check this but separately for group using the by statement. So if I use the by statement, class statement don't work with the paired statement, so hence we have to use this by statement if I want to check the impact across the group separately. So if I check this across group, see if I check this across group, this is the p-value for group 3, this is the p-value for group 2, fairly similar because there is not much variation across the groups. And if I check this here, we see it's significantly low, so is here. But if I look at the levels, I will probably say that in group 3 the increase is a bit high because the difference is a bit higher as compared to group 2. Okay, but both are highly significant change. So basically by paired t-test we can understand the impact or the impact of change in two variables. Now an example of this can be, say for example, here as we're saying that some kind of intervention of operation has happened, so before and after the operation what is the impact. Similarly for any kind of dietary regime we go into, we can check the impact of dietary regime in terms of the weight before and after the regime, or HR has done some kind of training, so before and after the training what is the impact on productivity. Some kind of ad campaigns have come up, so before and after the campaign what is the impact on the awareness of a particular product, or some export policies has been announced by government, and the impact of the export policies can be understood by checking the export level of different companies before and after the change in policy. So in a lot of scenario this paired t-test can be used. In fact these tests of hypothesis can be used in a lot of scenarios. So to sum it up, what we covered today is that first we, for one sample t-test is primarily used to check whether the mean of a variable is equal to a particular value or not. For example, I would like to check whether the average salary in a particular city is 30,000 or not. So for this the one sample t-test is what we use. Similarly, if I want to compare the mean of a particular variable across two independent population, we use the unpaired t-test or the independent sample t-test. So average salary same across Kolkata and Bangalore, we use the independent sample t-test. Similarly, for when we have more than two populations to work with simultaneously, say Kolkata, Bangalore and Chennai, then we have to use the ANOVA test. So that's the one way ANOVA for me. Now apart from one way ANOVA when we want to check the impact of two population groups simultaneously. For example, one is city, the other is gender, then we use the two-way ANOVA, or three-way ANOVA if we bring in another variable like educational qualification. And when we have this more than one-way ANOVA, we can also want to check the interaction of the combined effect through the combined effect code, which is the X star Y. Okay, so this way we can check the equality of means across different population subgroups, their combinations, using this ANOVA test, which can be a one-way ANOVA, two-way ANOVA, or two-way ANOVA with interaction. And finally, the pair T test, which can be used to check the mean of two variables, whether they're same or not. Again, the hypothesis is that the means are same, and H1 is they are not the same, and if we reject the hypothesis, we claim that they are not the same. Not only that, by looking at the sign of the change, we can say whether there is increase or decrease, and ideally the variable should be somewhere related. If they are not related, then the test doesn't make sense. Okay, so probably height of a group of children before having Complan and after having Complan can check the efficacy of the claim that Complan is making, that they increase the height of the children. So for these things, the pair T test can be used, and if I want to check it for different groups of a population, we can use the by statement before, but prior to that I need to sort the data by that particular variable on which I want to use the by statement. So to sum it up, this is what we had to discuss in today's webinar. If anybody has any question, they can ask me, and or you can mail it to our team at Ivy, and we'll be happy to clarify your doubts or any other further queries on this. And any other queries or anything, you are free to please mail us, and we'll be happy to answer your queries in terms of whether regarding to this webinar or the details of the course and everything. So please mail us to our email ID at Ivy.